Hi everyone, I'm Shouvik Roy Choudhury, currently a postdoctoral fellow at the Indian Institute of Technology, Bombay. I'd like to thank the organizers for providing me an opportunity to present my work at this conference. My talk is based on these two papers, both written with Steen Hannestad and Thomas Tran from Aarhus University. The first one is on neutrino self-interactions and the Hubble tension and has been published in JCAP. The second one on neutrinos and inflation is in preparation. This talk is divided in two parts. The first part is related to the Hubble tension based on the first paper. Let me start by introducing neutrinos. Active neutrinos have three mass eigenstates, which are quantum superposition of three flavor eigenstates: electron neutrino, muon neutrino, and tau neutrino. Tightest bounds on the sum of neutrino masses come from cosmology. In our work, we use the degenerate mass approximation, which works well with the current cosmological data. Here, we introduce an additional parameter, n effective, to parameterize the effective number of relativistic degrees of freedom other than photons in the early universe. For our purposes, these are only neutrinos. So in the first paper, we update the constraints from cosmological data on flavored universal neutrino self-interactions mediated by a heavy scalar of allowed mass higher than 1 keV, so as to be able to treat the neutrino self-interactions as an effective four-fermion interaction for the modes probed by the current CMB data. A heavy vector mediator also works. We consider a simplified interaction with a diagonal coupling matrix. As long as the effective self-coupling G effective is greater than the Fermi constant, the neutrinos will remain interacting with each other even after decoupling from the photons at a temperature of around 1 mega electron volts. The self-interaction rate per particle gamma is proportional to G effective square T nu to the power 5, where T nu is the neutrino temperature. So this interaction will stop neutrinos from free streaming as long as gamma is greater than H. Introducing this kind of interaction among neutrinos had shown potential in solving the Hubble tension in previous works in the very strong interaction range, where the coupling strength is 10 to the power 9 times the one that of weak interactions. This prevents neutrinos from free streaming even until the matter radiation equality. The cosmological model of interest here is an extended lambda-Sadian model with three additional parameters: n effective, sum of neutrino masses, and the logarithm of the coupling strength G effective. Using this model in the strong interaction range, Kreis et al. Had found a region of allowed parameter space with high G effective values accompanied with high N effective sum of neutrino masses and H naught, with the Planck 2015 low L and high L temperature and lensing data combined with baryonic acoustic oscillations data with similar goodness of fit to the data as lambda CD. In this model, N effective and H naught are positively correlated, and the solution to the Hubble tension came from N effective values of around 4. Planck polarization data was not used for the main conclusions. This model drew a lot of interest in the cosmology community. So with the public release of the final Planck likelihoods, we thought it is time to test this model against the new likelihoods. We first sample the parameter space using the full prior range of log G effective, which is from minus 5.5 to minus 0.1. Since the posterior of log G effective is bimodal, to obtain constraints for the individual interaction modes, we also divided the log G effective parameter space in the moderately interacting range, mi nu, and the strongly interacting range, si nu. So we run these analyses separately as well. We also run the non-interacting scenario denoted by ni nu, where G effective is 0. This slide shows the one-dimensional posterior distribution of various parameters for the runs using the full prior range of log G effective. In the lower left, you can see that all the dataset combinations lead to a two-mode posterior in log G effective. In the upper left, one can see that the strongly interacting mode also leads to a completely separate preferred region for theta MC, which is a parameter Cosmology uses for angular scale of the sound horizon at recombination. Now, if you consider the two plots at the right, they correspond to N effective and H naught. You can see that with temperature and low polarization data, low multiple polarization data, a very large region in the N effective and H naught parameter space is allowed. That is the TT plus low E data. And there is no conflict with the local measurement of the Hubble constant. However, as soon as we add the higher polarization data, the high N effective and H naught values are discarded. With the inclusion of the additional EXT data, which is basically Planck 2018 lensing, BAO, RST, and uncalibrated type 1 supernova data. So with this additional EXT data, the allowed parameter space gets slightly narrower. Thus, as you can see, with the most constraining data set, that is TTT-EEE plus low E plus EXT, we do not have a promising solution to the Hubble tension in this model. In this slide, we show the 1D posterior probability plots for runs where we had separated the moderately and strongly interacting modes. The red and green curves correspond to the strongly interacting mode, whereas the blue and the black curves correspond to the moderately interacting mode. You can see that the strongly interacting mode also prefers high theta MC and low NS values, which will be important later. This is because the changes in the amplitude and phase shift of the CMB peaks can be partially compensated by decreasing NS and increasing theta MC. Interestingly, as far as N effective and H naught go, the strongly interacting mode actually prefers slightly lower values of N effective and H naught than the moderately interacting mode, although there is no conceivable tension between MI nu and SI nu regarding the N effective and H naught values. Now in this slide, we show the 68% and 95% 2D correlation plots between various parameters. From the upper right plot, we see that N effective and H naught are strongly correlated in this model. And since N effective is strongly constrained by the high multiple polarization data, high values of Hubble constant that can solve the Hubble tension get discarded as well. So to summarize, log G effective is degenerate with theta MC and NS, and this allows for a bimodal posterior distribution even with the latest Planck likelihoods. With the TTT-EEE plus low E plus EXT data, we found for the strongly interacting mode, the following 95% bounds on your screen. As you can see, the neutrino mass bounds are quite robust in this model when compared to lambda CDM, which gives a sum of neutrino masses less than 0.12 eV at 95%. The preferred N effective values are slightly on the lower side, as we said before. But even if one were to reanalyze the data with an effective fixed to the standard value of 3.044, one would very likely get an H naught around the ballpark of 69 to 70 kilometer per second per MPC, which does not work as a solution to the Hubble tension, but it reduces the tension to some extent. Also, to be noted that this model does not do any better than the non-interacting mode in solving the tension. It is also to be noted that neutrino self-interactions are strongly constrained from particle physics experiments, with the exception of flavor-specific interaction among the tau neutrinos. This is again something that will be important later when we consider the inflationary models. So we found with the TTT-EE plus low E plus EXT data that the best fit chi-square difference of around 3.4 between the strongly interacting and the non-interacting mode, and also a Bayesian evidence ratio of 0.06. So both statistics disfavor the flavor universal strong interaction scenario compared to the non-interacting case. So to conclude, with current data, especially with CMB polarization data, this model doesn't look like a promising solution to the current H0 discrepancy, even though it reduces the tension slightly. So now we come to part 2, where I'll talk about neutrino self-interactions and its relation to a couple of inflationary models. The primordial scalar and tensor power spectra are usually parameterized with AS and AT, the amplitude of the perturbations, and with NS and NT, which are the scalar and tensor spectral and indices, respectively. We also have the tensor-to-scalar ratio as AT divided by AS. A general slow-roll single-field inflationary model has the Lagrangian of this form, where V phi is the potential. With it, one can define the standard slow-roll parameters, that is epsilon and eta. The cosmological observables, NS and R, can be derived from the slow-roll parameters at phi s, where phi s is the value of the inflation field 40 to 60 e-folds before the end of inflation. This is needed for observable fluctuations in CMB. Conventionally, inflation ends when the slow roll parameter epsilon becomes unity. And now, if you see the equation for the number of e-folds n star, you can calculate NS and R for a particular V phi and n star, given you get phi E, that is the end of inflation, from the epsilon equal to 1 equation. So in this work, we are interested in natural inflation and Coleman-Weinberg inflation. And these two have these potentials that you can see on the screen, where these lambda, A, F, and G, these are parameters of these models. And these models are both ruled out by current cosmological data at more than 2 sigma in the minimal lambda CDM model, lambda CDM plus R model, where we also consider tensor perturbations. We want to see if neutrinos can save them. In this plot, you can see how both the models are ruled out with current data. The area covered by the magenta lines is the prediction for natural inflation, whereas the black lines represent the Coleman-Weinberg inflation. Note that Coleman-Weinberg predicts very small values of the tensor-to-scalar ratio. Here, I want to mention that BK18 is the latest bicep-cake data on the CMB mode spectrum. Now, if we move to the non-interacting neutrino model, where we don't have any interactions, but we have an effective and sum of neutrino masses as model parameters, we see that the allowed parameter space is expanded, but the two inflation models are still disfavored at 2 sigma when all the data is included. That is the blue correlation plot. But of course, if we consider only the CMB data, then they can be they are included at 2 sigma. But now let's consider neutrino self-interactions as before, but this time with 2 changes. One change is that we have incorporated the neutrino interactions in both the scalar and tensor perturbations. And the second one is that we consider 2 scenarios. One where all 3 neutrinos are interacting, and the second where only 1 neutrino is interacting. The 1 neutrino interacting model is motivated from the constraints from particle physics, as I had mentioned before, where these kind of interactions are heavily constrained, except for tau neutrinos. So in this case, we find that both the 3 neutrino interacting and 1 neutrino interacting models allow these 2 inflationary models at 2 sigma. This happens because strong neutrino interactions induce changes in the CMB spectra that lead to lower values of NS. So this is, again, note that these are for full range runs of log G effective, because we want to include all the effects of the moderately interacting mode and strongly interacting mode together. Thank you.